Welcome, my name is Lazarus Agapidis and I'm a senior network engineer here at MORRELL Telecom. In today's video, we'll be going over IPv6. Now, IPv6 is a very hot topic these days. It is a new protocol, relatively new, that's being implemented as we speak. It has a lot of promise for the future and is being designed so that it'll function for the next decades and not just for a few years. So IPv6 essentially has been created out of a need to replace IPv4. So in order to look at IPv6 and understand it more fully, we'll start by looking at IPv4, how it was developed, what its weaknesses are, and how IPv6 comes to address these issues that IPv4 has. So IPv4 uses an address format that we've all come to know and love, and it's a format similar to this, 10.3.5.17. This is an example of an IPv4 address. Now, each of these numbers is composed of 8 bits, which means that this whole IP address is 32 bits. Now, 32 bits will give us 2 to the power of 32 addresses, which is approximately 4.2 billion addresses. Now, this is something that most people out there talking about IP version 6 refer to, that IP version 6 resolves the problem of the very few IP version 4 addresses that are available. Now, when IPv4 was designed in the early 80s, there may have been a few hundred hosts that had IP addresses at certain universities and at the Department of Defense of the United States. So 4.2 billion addresses was a very large number for the scope of the network that existed at the time. And if we really think about it, this IPv4 was designed in the early 80s, and it's into its 4th decade of existence. And that's really a great accomplishment. That really tells us that IPv4 was very well designed from the ground up and very robust. It was able, and it is still able, to respond to the needs of networking today. And if we think about it, IPv4 is not going to be replaced by IPv6 anytime soon. Both protocols will be functioning at the same time for at least another decade. So it's going to be, IPv4 will approach 50 years of usage before it's actually going to be retired. So IPv6, in contrast, uses 128 bits, which means that's 2 to the 128th power, which is approximately 340 undecillion addresses. Now, this number can also be expressed as 340 billion addresses. You can look at it in many ways to see how many addresses those really are. But essentially, for today's needs, what this means is that the address space is essentially inexhaustible. Now, this might not be true several decades down the road, but at least for now, that's a statement that we can really stand by, for the needs of today at least. Now, this limitation of IP addresses required several ways in which we can conserve addresses, and one very useful and widespread way is the use of NAT. Now, what NAT does is you have a router here and you have the internet here, and behind that router you have a PC. Now, this PC will have an IP address, a private IP address of 10.10.10.3, and then you might have another router on the internet, your neighbor, and you have another PC here which also has an IP address of 10.10.10.3. That means that both of these PCs have the same IP address, but that doesn't really matter because these routers do what is called NAT. They perform NAT, which means they'll translate this address to an external address such as 147.33 152.5.5. And it'll translate this address to 152.3.3.1, for example. These are routable IP addresses. These are essentially, that means that they can be used on the internet, and these are unique. You may have a lot of PCs behind here that have many different addresses, but all of these, when they go out onto the internet, they will use this one single IP address. Now, we won't go into the details of NAT, but what this essentially does is it allows us to use many internal addresses, reuse them for hundreds or thousands of hosts that we may have on the inside of our networks, and all those are mapped to 1 or 2 or 3 routable external IP addresses, thus keeping the address space on the internet smaller and maintaining the use of IPv4 for routing on the internet. So the first and most basic need that IPv6 comes to fulfill, the weakness of IPv4, is the number of addresses. Now, the interesting thing is that most people, that's what we hear most, because it is truly the most impressive and probably the most pressing issue. But there are a lot of other things that IPv6 offers that we don't hear that much about, and I'd like to express those as well, because those are also extremely important as the number of addresses as well. Now, one of those is security. IPv4 was not designed with security inherently in mind, because in the early 1980s, when it was developed, it was not something that was that important. As the internet progressed and as new ways were found by malicious users to be able to attack servers and services, there had to be ways of employing security. Now, because IPv4 doesn't inherently support certain features, such as security, a lot of companion protocols have been created in order to fill in those gaps. Now, for security, the companion protocol that has been developed is called IP security, or IPsec. Now, IPsec is not really a protocol by itself. It is essentially a framework that provides confidentiality, integrity, and authentication. Now, confidentiality refers to when I have my PC here and I'm sending you an email over the internet, and you receive this email, or whatever it is that I'm sending to you, there is no third party that's connected to the internet that can read this, that can intercept and read this information. So this guy here is unable to read what information is being passed through there. Even if I receive it, I will be unable to read it. So essentially what's happening here in confidentiality is encryption. Now, there are several choices that we can use for encryption. These are the encryption algorithms that can be used. And these here are the methods by which they are applied. Then we have integrity, which means essentially integrity will make sure that if I send hello, that the actual packet that is received here and reassembled and displayed on your screen is also hello, and it's not changed along the way, either by malicious users or by some errors that may occur. Now, there are various mechanisms and algorithms that can be used for integrity, which are shown here. Then we have authentication, which essentially, when I send you hello here, you can verify that it is me that's sending it to you and not someone else masquerading as me. Once again, there are various protocols and mechanisms that can be used. Now, all of these mechanisms use what is called the Diffie-Hellman algorithm, and there are various types. They use these algorithms in order to fulfill their function. Now, I won't go into more detail about IPsec, but essentially what's happening here is that there is an IPsec framework that has been created as a companion to IP, which is added in addition to the IP protocol and packets that are being sent. Now, what this actually means, it's a very well put together methodology, but what this actually means is that we're adding additional things to the IP packet. And here we can see what we're actually adding in one situation. Now this here is one example of the implementation of one of the mechanisms that we saw before. Here we have the original packet with an IP header, and we have a TCP header here from the higher layer protocol, and we also have the data. So this is an IP packet without any security, without anything sent over the network. Now, if we're going to apply some sort of IPsec mechanism, then we're going to have to add some headers. That means that to the data, which is this here, we're adding an ESP header, an ESP trailer, an ESP authentication trailer, and then adding on the IP header at the beginning. Now, what we have here is we have this part of the packet being encrypted and this part of the packet being authenticated. Now, there are other modes, other implementations that can be used. In this case, we have another example where we have this part of the packet being encrypted and this part of the packet being authenticated. This is just another implementation of an IP security option. But what I want to show here is that in order for IP, which is this here, to employ security, you're adding on additional companion protocols that will do this here and this here. So it is more complex, it is more not as elegant, but it works, and it has been working for decades. IPv6 has come essentially to make all of this simpler, and it has incorporated IP security as part of its implementation. So it's no longer something that's added to IP, but it's something that is inherently part of the protocol itself. Now, another issue with IP version 4 is that usually when you have a network, you have to actually go in and configure certain things. So if I have a network at home where I connect a PC, I have to go into that PC and configure its IP address, subnet mask, and so on. Or if I have a home router which is connected to the internet, that home router can give an IP address automatically to the PC so that I don't have to actually do that. But you still have to go into the PC and say, please automatically configure. Now, a lot of devices today are network devices, devices that traditionally were not network devices. For example, a TV. How do you go into the interface of a TV and configure its IP address? And why, if someone who's not a network expert buys a TV and they want to actually get that working, what's an IP address? So IPv4 actually needs you to go in and actually, even trivial things, go in and configure that network interface. IPv6 allows the automatic obtaining of IP addresses and network information without having to touch anything. You just plug it in. It's truly plug and play. And that's one of the major advances of IPv6, and we'll see how that works. We'll look at one more weakness that IPv4 has that IPv6 has come to resolve, and that has to do with the way that broadcasts and multicasts are managed on a network. Now, on an IPv4 network, we'll have a switch where we'll have several PCs connected to it, and there are some functionalities, some network services that require broadcasts. Now, if this PC wants to receive an IP address from a DHCP server, it will send out a broadcast on the network. Now, if this is then connected to a router, the router is actually the boundary of the broadcast domain. So any broadcast sent by this PC will be received by all of the devices on the network. The DHCP server, if the broadcast is a DHCP request, then the DHCP server will be the one that will respond, and everyone else will just have to drop that specific packet. Now, this functionality is inefficient because a lot of services, not only DHCP, but other services as well, use broadcasts. And that means that a lot of devices on the network will be receiving packets that don't belong to them. They still have to open them though, process them, see that they don't belong to them, and throw them out. That takes up CPU cycles, and that means that it's less efficient on the network. IPv6 comes to resolve this by actually eliminating broadcasts completely and replacing them with multicasts. Now, a multicast communication is one where we have a single device that sends to multiple destinations, but not to all destinations. So IPv6 uses multicast instead of broadcast for such functionality, and it does so in an ingenious way so that that communication that otherwise would have been functioning as a broadcast under IPv4 is functioning as a multicast in IPv6. That dramatically reduces broadcast traffic, well, essentially eliminates broadcast traffic on any network segment, something which drastically improves the efficiency of the IP protocol being used. So just to review, we've looked at various weaknesses of IPv4, the most apparent, which is the limitation of the number of addresses. We've looked at the fact that it does not have an inherent security component and needs companion protocols in order to function. We've seen that IPv4 doesn't really have an auto-config situation where where you can configure household devices that connect to the internet, such as TVs or thermostats or washing machines for that matter. It doesn't have an inherently pure plug and play mechanism, and it also it does not have a very efficient use of the network when we talk about broadcasts. So these are some of the fundamental weaknesses of IPv4 that IPv6 has come to resolve. Now let's go straight into a description of IPv6 to see what this protocol really is and the advantages that it has. Now, as we mentioned before, an advantage is the number of addresses. Now, what practical result does this have? This essentially says that if we have on the internet, if we have a router, with IPv4, typically behind this router we'll have a switch, and behind this switch we'll have a multitude of end devices. Now, each of these end devices under IPv4 usually would have a private address, and you'd have NAT running on the router. Here with IPv6, each of these devices will have a routable IPv6 address, which means that this PC can be uniquely identified by any device that's on the internet. So if I'm somewhere on the internet here and you're here behind this router and I want to communicate with your PC, I just have to put in your IP address, your IPv6 address. So this is an example of an IPv6 address. And we'll get into details about what all this means in a little bit. But I can send you information directly to your PC without having to configure any NAT, port forwarding, or anything like that. Now, this is fantastic, especially for services such as IP telephony, services such as setting up a web server on the internal part of your network, having you connect to any internal device on your network, which is something that was not doable because of the fact that you had NAT running on the router here. And you'd have to put in complex port forwarding configurations in order to get that to work. Another problem that NAT brought about was issues with cameras, IP telephones, video servers. All these things required you to be able to go through this router and get to the final destination via NAT. Now with just a simple IP address, you get to resolve all these issues and get directly to that device. Now, this does open up an issue with security. NAT was a physical obstacle for some security threats, even though NAT itself wasn't designed for security. It did bring about an obstacle for malicious users to actually get into your internal network. Now, that doesn't mean that IPv6 is not secure. It just means that you'll have to implement the appropriate security in combination with that. Now, concerning all of the additional capabilities that IPv6 has, such as security, auto configuration, broadcast, multicast, and so on, the major difference in architecture for IPv6 that allows all these things is the extension header. Now, a typical IPv6 header looks like this. We have the version, which states that it's IPv6, traffic class, which deals with quality of service, flow label, which also deals with quality of service, payload length, which has to do with essentially stating how big the payload is. Then we have the source IP address and the destination IP address, and we can see that these are quite large because they're 128 bits each. That's essentially 16 bytes each. So these two together are 32 bytes. So that's quite a big header. Now, I'd like to draw your attention to the next header field here. Now, what this field does, and this is really what really excites me about IPv6, it's the fact that this field tells us if there is what's called an extension header added to this header. There are various types of extension headers, and each extension header does something specific. And I'd like to draw your attention to the security extension header. Now, if this value is set to 0, there's no extension header, so this is the whole header of the IPv6 packet. But if this extension header has a code in there that states that, you know what, there's an extension to this header which has information about security, then all of a sudden we have another section here that refers to issues concerning security. So this here is an example of an IPv6 packet with an extended header. So we have a code here, and if we look at this header here alone, that's equivalent to this part here, which is just the regular header without anything else. So a next header code of 0 states that the next header is a hop-by-hop options header. This is an option, an extended header that helps in routing. And then we're not limited to just one additional header, but we can have in this header a next header indication of 44, which states that we have another header coming after that, which is a fragment header. Now, this header helps deal with fragmented IPv6 packets, making their reassembly more efficient. Now, if this next header had the code for security, then we would have another header here stating that we have another extension that indicates what kind of IPsec security we're going to implement. And here we would state the various options that we have for IPv6. And then finally, the last header, if it has a code of 6, that states that the next portion of the next thing that's coming is actually the TCP segment that has been encapsulated in there. So these extensions essentially provide additional mechanisms, additional functionality to the IPv6 packet. And these headers are used by routers in order to be able to manipulate and use the packet and perform based on whatever information is found in there. Now, there are various types of headers, and if we have a header code of 51, then that means that the next header that's coming, then the extension that's coming, has to do with authentication. And if it's 50, then the next header that's coming has to do with encapsulation. So these two extension headers essentially encompass all of the IPsec architecture and mechanisms within the IP version 6 packet. Now we can see here additional headers that are available with header codes for routing, for destination options, for fragments, for additional destination options, for mobility, which is a very important part, which has to do with smartphones and devices that go from network to network. Or if there's no additional header, no next header, then the code is 59, stating that that's the end of all of the headers, extension headers that are there. Now notice that there are essentially 9 types of headers, but the header code is quite large. And if I'm not mistaken, that the header code is 8 bits. So we have up to 255 next header codes that can be used. So the IP version 6 protocol is very expandable in this aspect. Now, one of the major advances of IPv6 is the fact that hosts are able to configure themselves, essentially. If we have a network and we have a PC connected to that network and it is IPv6 enabled, what that will do is, even if there's no DHCP service, even if you haven't gone in to configure it at all, it will self-configure an IPv6 address called a link local address. Now, this linked local address is used in order for the PC to connect to any local routers that may exist on the network. That address essentially is created by various algorithms. That could be, it depends really on the operating system that is being used. It could be created using the MAC address, could be randomly generated, but in any case, it's an IPv6 address that is a linked local address. It's created and can be used only on the local link. That's why it's called link local. Any communication outside of that local link, for example, onto the internet, is impossible initially. Now, this link local address will allow the device to send out some packets to say, hey, I'm here, is there an IPv6 router on this segment, on this network? And if there is, then the router will actually respond and say, hey, I'm the router, I'm configured on your network in order to be the default router. So here is some information, here's a prefix, here's a my address. And through this communication, the PC here will be able to obtain internet connectivity. So the router will actually give a second IPv6 address to this called a global unicast address. Now that address is another IPv6 address. So essentially, it will obtain 2 IPv6 addresses, the link local address and the global unicast. The link local is used for local network housekeeping, while the global unicast is the unique IPv6 address that is going to be used for that device to connect to the internet and for other devices on the internet to connect to it. Now, this process, without getting into too much detail, essentially involves what is called a router solicitation message. So the device here will send a router solicitation message onto the network. This is a multicast communication, and it's sent to only routers that exist on the network. So this router will receive the router solicitation and will respond with a router advertisement, giving the information, the basic connectivity information to this device. So IPv6 equips network devices with fundamental communication in order for them to go to the next step of obtaining the global unicast address. So that's why you can have an IPv6 TV, plug it in, it'll find your router, it'll find connectivity to the internet, and it'll start functioning without any of your intervention. Now this is important as more and more devices are becoming network aware. Thermostats, air conditioners, washing machines, and every kind of electronic device in your home, in your business, will eventually get an IP address. And if it has connectivity, it's capable of being controlled over the network. So this is one of the fundamental advantages of IPv6. Now we can't have a video about IPv6 without actually looking at the IPv6 addresses. Now this here is an example of an IPv6 address. It is actually written in hexadecimal. It is not written in decimal. That means that each one of these 4 digits corresponds to 16 bits. And each individual digit corresponds to 4 bits. If you're not familiar with hexadecimal, look it up. There are a lot of resources online that explain exactly what it is and how it works. But it is what is used to represent IPv6 addresses. Now this address is written out as 8 groups of 4 hexadecimal digits, and if you have 8 times 16, that's 128 bits. Now this is daunting at first when you look at it if you haven't had any experience with IPv6, but as you get more familiar with it, it begins to make more sense, and it's actually quite intuitive compared to IPv4. Now this representation can be simplified further in a process called address compression. Now the first rule of address compression is that you can take these strings of zeros and replace them by 2 colons. So this would actually become this. You can see here that these 3 strings of 4 zeros have been replaced by 2 colons here. That drastically reduces the size. Now another rule that we can use is that anything that has any string of 4 zeros found between colons can be replaced by a single 0. So that means that we can take this and further reduce it to this. So you see that this here has been replaced by a single 0 there. So that's a lot smaller and a lot more manageable. Now these are the fundamental rules of address compression, and one more very important one is the fact that you can only do the double colon once. You can't do it twice on the same in the same address, because then it becomes ambiguous. So if you have multiple strings of zeros, you can't have double colon and then another double colon somewhere in the address. It can only occur once. So you have to choose which one you're going to replace. Now these IP addresses come with prefixes. IPv4 has the subnet mask. IPv6 has what is called a prefix. The logic is the same, but prefixes are always written as in slash format. So here we can have a /64 prefix, which means the first 64 bits are what's called the prefix, which in IPv4 jargon is the network portion, and then the next 64 bits are the interface identifier, which in IPv4 is the host portion. So essentially this is a lot easier because you don't actually have to do a lot of subnetting. So here's another example of an IPv6 address, and I'm showing this completely extended without any abbreviation, just for clarity. Now the /48 essentially tells us that we have 16 plus 16 plus 16. We have this portion of the address as the network portion, or the prefix, which belongs to the whole subnet. And then we have the rest of the bits here available as the host portion. Now one thing we will notice here is that if I have a prefix of /48, that means that I have another 72 bits available for hosts. It gives me many host addresses. It gives me a subnet which is larger than anything I will ever use or anything I will ever need. But we're not worried about wasting anymore, because even with a /48, we're able to have enough subnets to accommodate everyone. So there's no problem in wasting addresses. I know with IPv4 we're used to being careful with conservation of addresses. Even on internal addresses, we do it as a way of thinking. But in IPv6 we don't need that anymore. We can even create a point-to-point link between two routers on our network without having to create, like we would usually create a /30 subnet for that. In IPv4. Here, we can still keep the /48 and have 72 bits available for us and still only use 2 of these addresses without having any problem with IP address conservation. Now, this is another important aspect of IPv6, the fact that we're able to avoid any variable length subnet masks. We can have the same subnet mask length for all of our IPv6 addresses. With IPv6, we use the term prefix. So we can have the same prefix for all of our IPv6 addresses without having to really worry about variable length subnet masks and so on. So it's very, very easy, very straightforward to create all of your subnets in your network using the same prefix for all of them, without having to do complex calculations. So that's one major advantage of having so many IP addresses, is the design aspect is made a lot simpler. Now, as we mentioned before, IPv4 isn't going anywhere anytime soon. IPv4 will still be with us for a long time, and because of that, we have to find ways in order to allow IPv4 and IPv6 to function simultaneously. We have to be able to translate between IPv6 and IPv4 networks. We have to be able to connect two IPv6 networks over an IPv4 network. It depends on our ISP, depends on our equipment, depends on a lot of things. So because of the fact that the transition period is going to be well over a decade, it's important to know that it is possible to translate or to have these two protocols coexist. Now, IPv4 and IPv6 are not compatible, but there are methods by which they can coexist on a network. Now, one example of where IPv4 and IPv6 need to work together is this here. If I have at my headquarters an IPv6 network, I'm a company that decided to go for IPv6 and use all the advantages internally on our network. And we have a remote branch that does the same, IPv6. But the ISP that we're using, or the connection between these two locations, is still using IPv4. It hasn't been migrated or upgraded to IPv6. How can we allow these two to communicate? What we have to implement is something called 6-in-4. What that means is essentially we're placing an IPv6 packet inside an IPv4 packet. So anything that is communicating in here remains IPv6. We have a router here which is configured to do this IPv6-in-4 encapsulation. So any packets going this way and reaching the router will have added to them an IPv4 header and will be sent over this IPv4 network. So essentially they'll carry as a payload the IPv6 packet. Now this IPv4 network doesn't really care what the payload is. It only takes into account whatever's in the very first header, the IPv4 header. So that IPv4 header is used to route the packet to router 2, and that router 2 will de-encapsulate the packet and will send out the IPv6 packet. Now I've been doing this backwards because the diagram shows the communication going that direction. The communication in this direction is exactly the same. Now, this same thing can happen if we have an IPv4 network internally and we have an IPv6 network externally. That would be called a 4-in-6 encapsulation. So you would start with an IPv4 packet in your network. You would then encapsulate it into an IPv6 packet on its way out, and then it would be de-encapsulated back to an IPv4 packet on its way into the network there. So this is called tunneling, and it's well established, and it is used for such situations. Now, another mechanism that's available is called NAT64. Now, what NAT64 does is it essentially does the same thing as NAT, but instead of translating from private addresses to public addresses, what it does is it translates from IPv6 to IPv4, or vice versa. So if you have two networks, regardless of whether they're on the internet or on your own network, you can and one network is an IPv6 network, the other is an IPv4 network. You can actually allow these two to communicate with each other using a NAT64. So any packets going from host 1 will reach here with an IPv6 source and destination address, and then the NAT64 router will translate that to an IPv4 packet that uses IPv4 IP addresses, and it'll get to the host there. As far as host 2 is concerned, the host sending its information is an IPv4 host, and it understands and can communicate with it in that way. The same thing happens on the way back. The NAT router will translate from 4 to 6, and it'll go to host 1 as an IPv6 packet. Now, although it is called NAT, it doesn't function exactly as traditional NAT does, because traditional NAT will just replace the IP address in the header of the IPv4 packet. Here what we're doing is we're actually replacing an IPv4 packet with an IPv6 packet and vice versa. But the name is still NAT, and it is appropriate because it is a translation from one address space to another. So it's important to know that these technologies exist for both IPv4 and IPv6 to coexist in the world, on the internet, on internal networks, and each situation requires a specific type of solution. So these are solutions that exist in order to allow the two protocols to interoperate. So where are we now as far as IPv6 adoption on the internet goes? Well, this graph shows us the use of IPv6 between January of 2009 until April of 2019. So right now we're somewhere around 25%. Now that shows us how far we still have to go. Now, since around January of 2014, we've had almost a linear increase, which means we're up at 25% in about 5 years. If this linear increase continues, then we're slated to go full IPv6 sometime after 2030. The hope is, though, that will not remain like that, but it will eventually start increasing exponentially as the advantages of IPv6 are becoming more and more understood, as the capacities of IPv4 are becoming more and more taxed. And I believe that there should be some future event that will make that go up exponentially. But it gives us an idea of how important this usage of IPv4 and IPv6 together is. Now, this information has been taken from Google. If you do a search for IPv6 adoption in Google, they'll give you this graph is one of the first things that shows up. This is a worldwide graph. You can actually go in and check by country. I suggest you go into Google and do that search and take a look at your home country and see where you're at right now. Until now, we've been talking about IPv6 and how it functions and some of its capabilities. Now I'd like to focus a little bit on some of the innovative ways that people have been able to find for using IPv6. Now, we usually think about IP addresses as addresses used for hosts. But the truth is, because there are so many IPv6 addresses, we can have many addresses available on a single host. Now, Facebook has been a pioneer in this usage of multiple IPv6 addresses. Here we can see the structure of their data center. What they have is, we have multiple layers. We have, first of all, the rack. A rack is composed of several switches and several servers, which might be running virtual machines. Each rack is provided with a /64 subnet. That's 2 to the 64 addresses per rack. That's a lot of IP addresses, IPv6 addresses, keeping in mind that the whole of the IPv4 address range is 2 to the 32. That's all of IPv4. And here we have Facebook giving a 2 to the 64 address space to a single rack. Now, these racks are organized into what are called pods. So we have a whole series of racks here that are organized into a single pod. So you might have 10 racks per pod, and each pod is provided with a /59 subnet. Now, several server pods together will create what is called a cluster, and the cluster will be given a /52 address space, and a whole data center is composed of several clusters, so the data center is given a /48. So here we have several layers of the data center where each layer, each component is given a separate prefix. Now, each rack is provided with a /64. Now that /64 will be distributed among multiple virtual machines. There may be hundreds or even thousands of virtual machines that obtain an IPv6 address. But what Facebook does, and this is the really innovative part, they actually have IPv6 addresses that are used to reference virtual machines. They are used to reference specific user accounts. They are even used to reference individual photos and individual media. So you might have uploaded a picture on Facebook of you smiling, and what Facebook has done is it has taken this picture and it has referenced it with an IPv6 address. So when someone is viewing your page through the web, what they're actually doing is they're referencing a photo that has an IPv6 address. So IPv6 is no longer being used just for hosts. It's being used for media, it's being used for photo, it's being used to reference specific subfolders. So this is really fundamentally innovative. Now here's another example of how IPv6 is being used to reference specific content rather than hosts. Imagine you have on the internet a video, maybe on YouTube or hosted somewhere else, a video that is about 2 gigabytes in size. Now you can have a URL point to that video and then have that video be streamed to you. But using IPv6, you can, if you choose, break up that video into small little 2 megabyte pieces. That would mean that it would be composed of 1,002 megabyte pieces. Now each of those 1,002 megabyte pieces can have an IP address reference to it. So here we have a text file that is configuring a frame rate, that is configuring a specific bandwidth, that is configuring a specific duration, a time scale, that is telling your computer where to go and find all of those 2 megabyte size pieces. And it's going to pick them one at a time, download them, and then put them together and show them to you. Now, the important thing about this is that you can have all of these different pieces exist at different areas of the network in the whole world. So I might take the first piece from a server in France, another piece from a server in Belgium, another piece from a server in Canada, or depending on what is closest, or depending on what is fastest at that specific time. So this video doesn't reside on one specific server somewhere out there, but it might be broken up into a lot of different pieces and just reassembled at my computer. This vastly increases the efficiency of the internet, because you can actually have this video reside on many servers, and depending on where you are, you will access something different, a different location, even though you're using the same IPv6 address. Now, extending this concept even further, we can replace the whole URL structure with a single IP address. For example, traditionally when we view a web page, we have a URL that corresponds to a specific web page, which then references other media to place them appropriately on the page, so that you have the text where it has to be, you have the photos where they should be, you have the videos where they should be, and it's all put together on your web browser. Now, in order to be able to do this, you have various components of the URL. You have the DNS. First of all, you have the protocol, the HTTP being used. You have the DNS, which corresponds to an IP address. Then you have the port number, which usually is port 80 for HTTP. If it's not, you can actually specify what it's going to be. And then you have some directory path which shows where on the server the information you want exists. Then we have the file. Now that could be either an HTML file, it can be a PHP file. And then we have some additional options that come in here that tell us where we have to go in order and what has to be shown on the web page. This then in turn calls upon the various images and media that are embedded in the web page. Now, here we see a lot of different technologies being used together in order to get this to work. Now, if we were able to have this idea of an IPv6 address corresponding to content rather than a host, where we could say that this here, chapter 2, it corresponds to a specific IPv6 address, then we wouldn't need TCP port, we wouldn't need directory path, we wouldn't need a file, we wouldn't need separators, we wouldn't need all of these additional capacities, these additional functionalities. We would just need one IPv6 address, which corresponds to the content object, which in this case is an anchor, chapter 2, of a specific page. So with one address, we'd be able to access that specific content. So essentially what we're saying here is that IP addresses don't correspond to hosts anymore. They don't correspond just to hosts anymore. They can correspond to content, to pieces of data, to pieces of videos, to pieces of text that exist within a server found on the internet. In this way, what we're doing is we're taking one addressing scheme, IPv6, and using it to reference everything, simplifying connectivity and simplifying addressing of specific content. Now, to finish off this video, I'd just like to share a bit of trivia with you. A lot of people are asking, okay, we have IPv4 and now we have IPv6. What happened to IPv5? Well, IP version 5 was used for an experimental project called Internet Stream Protocol. Now, this was originally defined way back in 1979 and was later finalized and officially published in 1995 as RFC 1819. And if you're interested, you can look that up on the internet. It was never officially called IPv5, but it did use this designation to distinguish its packets from normal IP packets. And in order to avoid any confusion with this specific protocol, it was decided that IPv6 would be the official name of the new IP protocol. Well, this is an overview of IPv6. I hope that it has been helpful. I hope it has been informative. I hope that it has brought you to a point where you know more than you knew about it before. You learned something new, and maybe it gave you an opportunity to think about a few more things that you can research to further find out and understand IPv6. I hope that this has been informative for you, and I'd like to thank you very much for viewing.